Hello and welcome back to the channel Understanding Concepts of Physics. In case you haven't subscribed the channel yet, kindly do so and keep following the video from the playlist. There is an order in all the videos. Probably you won't be able to follow if you are just selecting a one particular video out of the entire setup. Okay, so we have been doing types of processes since a few days, and we have done isobaric, isochoric and isothermal process, which you might find out in the playlist. Today we are going to do something called as an adiabatic process, as you can see on the screen. Adiabatic process is a process in which the heat is kept constant. So Q is standing as heat, and if heat is kept constant in a process, it is called as an adiabatic process. So that's what the definition says. A process in which heat is kept constant is called as adiabatic process. A process in which heat is kept constant is called as an adiabatic process. So the technicalities of this process is heat is constant. So heat is constant. So if heat is constant, the change in heat is zero. So there is no changes in heat. That's why heat is constant. And you know the equation of first law of thermodynamics, that is dq is equal to du plus dw. So if dq is equal to z to 0, then this du or this dw can be brought on the other side. So you will get du is equal to minus dw. More on this just a few lines below. Here the temperature is not constant, so change in temperature is non-zero. Change in temperature is non-zero, so change in internal energy is non-zero, and change in volume is also not zero, so change in work done will also be not equal to 0. So this is the technicalities of an adiabatic process. Now let's get quickly into what first law of thermodynamics has to say. So by first law of thermodynamics, we know that dq is equal to du plus dw. So if du is 0, which I am putting over here, dq is 0, so this is 0. And if I just bring this dw on the other side, this plus will change to minus. So I'll get du is equal to minus dw. So this is one of the relations we get in adiabatic process. Now we are here to find out the work done in an adiabatic process, okay, how much the work done would be. So as we know that in thermodynamics, this is one of the relations which we have been using in all three processes in the previous video, that is dw is equal to pdv. So in order to find out the full work done, we'll have to integrate this. So what we do is just replace this p. Now just be careful with this equation. We are not discussing how this equation comes over here, and maybe this is a part of some other video we can discuss in coming few days. PV raised to gamma is equal to constant, and this is only valid for an adiabatic process. So this adiabatic process follows this equation which says PV raised to gamma is equal to constant. Now this gamma is the same ratio of specific heats, that is specific heat at a constant pressure and specific heat at a constant volume. So this ratio of specific heat, which we have already done in the topic called kinetic theory of gases, is the same gamma. It is sometimes also called as an adiabatic ratio. It is also sometimes called as an adiabatic ratio, or it is also called as ratio of specific heat. Keep the pressure on one side, take V raised to gamma on the other side. So constant upon V raised to gamma, this is something we get. Put P ka value over here. So what remains is dW as it is equal to C as it is. Wherever there is a P, put the value of C upon V raised to gamma. So this comes out to be C upon V raised to gamma dV. So now let's start to integrate, because we have only two variables here, dW and volume. So integration on both the sides. So integration on both sides, limit goes from 0 work done to the full work done W, and volume limit goes from initial volume to final volume Vf. C upon V raised to gamma as it is, dV as it is. Now from the rules of integration, we know that the constant terms can be thrown outside, so that C comes outside. So C comes outside, and in the next step what we have done is we have taken this V raised to gamma in the numerator. So because v raised to gamma is positive over here, it will become a negative v raised to gamma, v raised to minus gamma. Now what are we going to do is we are going to use the standard forms of integration. So integration of dw is w, integration of v raised to minus gamma is v raised to minus gamma plus 1 upon minus gamma plus 1. Now in case if you do not follow, the few a minute or two is dedicated for how to get that. Now integration of dx is as good as 1 dx. You can write 1 anytime at any point of time, and this 1 can be written as x raised to 0. So I have written as x raised to 0 because anything raised to 0 is 1. Anything raised to 0 is 1. So 1 can be written as x raised to 0. Now using this relation, that is the standard form of the basic integration formula, integration of x raised to n dx, you will get x raised to n plus 1 upon n plus 1. So because I have a 0 over here, it is 0 plus 1 upon 0 plus 1, which is equal to 0 plus 1 is 1, so that is 1, and 0 plus 1 is 1, so that is 1, and 1 we do not write it, that's why we say x. In case if you are not so inclined towards mathematics, I would suggest you pause the video and go through this white colored writing, in case you have not so inclined to mathematics. In case if you are inclined to mathematics, you can just move forward. Now this work done, I need to get rid of these limits. So how do you get that? You have to put upper limit minus the lower limit. So wherever there is a w, there is an upper limit. So in place of w, there is a w, this is w, and minus the lower limit. The lower limit is 0, so that is a 0. C upon, now this minus gamma plus 1 is a constant, so that I'll move outside, and instead of writing minus gamma plus 1, I would write 1 minus gamma, just shuffling 1 minus gamma, that's a constant, that's outside. You can shuffle that because I don't want a minus sign in my starting term. Now then I need to get rid of the limits in this particular case as well. So v is the variable, so wherever there is a variable we'll put an upper limit vf, minus wherever there is a variable we'll put an initial. So I'll get vf minus gamma plus 1 minus the lower limit, so vi minus gamma plus 1. So upper limit minus lower limit. Now w minus 0 stands as w equal to 1 upon 1 minus gamma. I have taken the c inside, so c multiplies here, c multiplies over here as well. Now there is a mathematical play over here. What you can see is pv raised to gamma is equal to constant. This is valid for adiabatic process, and this I have not proved it because it's not a part of this particular derivation. We are just using that equation. So if the product of pressure and volume raised to gamma is a constant, then any value of pressure and any value of volume, the product of that will remain constant for an adiabatic process. So final pressure, final volume raised to gamma would be equal to initial pressure, initial volume raised to gamma is equal to constant. So any two values of pressure and volume the product of that will remain constant for this adiabatic process. Now why I am doing this is wherever there is a vf, I'll put this value, and wherever there is a vi, I'll put this value. So let's put that. I have followed the color pattern, so in case you can, if you are not following, you can just go through it. So w as it is, 1 upon 1 minus gamma as it is, bracketed. Now wherever there is a c, I'll write pf vf, so this is pf vf, and wherever there is a c, I'll write as pi vi. Now if you can see, this is v raised to gamma, this is v raised to minus gamma, and this is v raised to 1. So if the base is same, you just add the powers. So gamma minus gamma plus 1, so plus gamma minus gamma gets cancelled, and you remain with v raised to 1, and 1 we don't write. So I get 1 upon 1 minus gamma as it is, pf vf as it is, pi vi as it is, and that's it. So this is what work done for adiabatic process is. So normally we derive it till this point, but yes, we can go ahead and we can also have an equation with temperature as well. So let's see. Also, PV is equal to nRT. This is an ideal gas equation. So I can just say final pressure, final volume will have final temperature. N and R are constant, so they will not change. Same way, I'll create an equation for initial as well. So final is created, initial is created. Now, PFVF minus PIVI, I'll put the values here as PFVF and PIVI as nRTF, nRTI. So value has been put, nRTF, nRTI. Now, nr is a constant, nr is a common, so I'll take nr outside. So nr comes outside, 1 minus gamma as it is, and tf minus ti remains. So this is an equation with which contains temperature, and this is an equation which contains pressure and volume. So this is what it is. Also, I have just mentioned about this equation in my previous screen, or just at the beginning of the video, that is du is equal to minus w. So if I put the value of w, I'll get this equation, particular equation. If I move this minus sign inside, ti will be, which is negative over here, will become positive, and tf, which is positive over here, it will become negative. So that's why you see there is a minus sign here and there is no minus sign here. And the key difference is this is tf, this is ti, and this is ti, this is tf. So that's the main difference between that. So that's one thing. Also, if you are planning for entrance exam, you can just note this part. I mean, this is a concept actually. After an adiabatic expansion, like bursting of a balloon or bursting of a tire, after an adiabatic expansion, the gas actually cools down, and after an adiabatic compression, the gas actually heats up. Now that is why does that happen? You figure it out for yourself, and just let me know. You can use this equation, you can use this equation, and just let me know in the comment section, okay, why does the gas actually cools when there is an adiabatic expansion. Okay, it's a very easy answer. In case if you want to follow some trail, then I would give it like this, that because du is equal to minus dw minus w, so this is the equation which will lead you to this kind of expression. Once you get it, you will really find it. Lastly, the PV graph. So PV graph is pressure on the y-axis, volume on the x-axis. A is the initial position, initial state. B is the final state. This is VI, this is PI, this is VF, PF, final pressure, final volume, final initial pressure, initial volume, and the graph would be a curve. But note that this graph would be steeper. So like suppose if I have pressure and volume graph for isobaric process, it would be straight. This is isobaric process. For isochoric process, I would be saying that it would be a vertical line. For adiabatic process, it would be something like this, and isothermal process is something like this. So this is isothermal and this is adiabatic. Now note that the difference between isothermal and adiabatic is that adiabatic is a steeper curve. It just goes down very quickly compared to isothermal process, which goes down gradually. So isothermal curve would look something like this, and adiabatic process looks something like this, which is a steeper curve, like its slope gradually its slope is much higher at this point. So this is what adiabatic process, all about adiabatic processes. I know the video is long, but the derivation was too. Thank you so much for watching. In case if you are still with me, subscribe the channel in case you haven't done so, and please go through the other videos in the playlist. Follow the playlist in order to understand in better manner. Thank you so much. Bye.